All right, so we have a stone being dropped onto soft ground. You may assume that its velocity is small enough that drag is not significant. Okay, so like we are dropping it from maybe a meter or two above the ground. In the diagrams you draw for this question, carefully represent the magnitude and direction of the forces. Okay, so we have to draw forces of larger magnitude to be longer arrows, etc., etc. Okay, now if we're going to draw a free body diagram of the stone for A just before it hits the ground. Okay, so A, free body diagram, stone just before it hits the ground. If there's no drag and it's not touching the ground and we've already dropped it, well, then there's only one force, gravity, right? That's our only force at a distance. There has to be contact for any of the other forces. All right, B, draw a free body diagram of the stone after it has contacted the ground and is slowing down. Okay, so this is sort of in that fraction of a second where it's touched the ground and hasn't quite come to a halt yet, right? It's squelching into the mud or whatever this soft ground is. And so we need to draw our little stone. Force of gravity is still going to be there. I'll try to make it roughly the same length as the other one in part A. But now there's going to be a normal force from the ground upwards, okay? And if the stone is slowing down, we know that, well, okay, so its velocity is down. So that means that the acceleration would have to be this way if in fact v is getting smaller. And so we need a net force that is upwards. So this upward normal force on the ground, we need to draw to be bigger than the downward gravitational force, okay? And for C, draw a free body diagram of the stone after it has come to rest on the ground. Okay, so come to rest, so acceleration is now 0. And there's our stone. And I'll again try to match the length of the gravity arrow. And that means if acceleration is now 0, then the upward normal force on the ground just has to be equal in magnitude, opposite in direction, and that's what we've got there to the best of my abilities drawing it anyway. And lastly, D. Draw a free body diagram of the Earth in your written work showing the forces that result from its interaction with the stone. State how these relate to the forces acting on the stone. Equal to, greater than, unrelated, etc., etc. Okay, so the Earth, let's make it a little bigger. Here we are. Not really to scale, but let's see. So the stone is interacting with the Earth at a number of different points here, but let's encompass both the normal force, so the contact, plus the gravity. And we know that if the stone is being pulled down by the Earth, then the stone is pulling up on the Earth with its gravity in the opposite direction. Equal and opposite, third law, right? Third law pair. So I'll just call it negative F sub g. And I should be drawing it to be the same as that one there, okay? Or any of the F sub g's in A, B, or C. And then also, if the Earth is exerting a normal force on the stone, then the stone is exerting a normal force on the Earth. And so there'll be some downward normal force. And this one, I'm not too particular on the length of it because we have a couple of different situations in B and C where there's a normal force and it's different. So, but I'll just put it in there. And I'll note that here, okay, F sub n, oh, sorry, this should be negative F sub n, okay? Equal and opposite. And negative F sub n our third law pair. So this, in other words, and this. And let's see, let's grab a different color here. Blue. In the case of this one and this one, they are also a third law pair, as sort of my F sub g and negative F sub g nomenclature implies. And so what this means, right, the third law pair part means equal and opposite. Must be Newton's third law, okay? So that's the relationship between them. Okay, that's more or less what I was looking for. You didn't have to be quite that verbose, but hopefully that helps you understand if you didn't quite get some part of this. All right.